All right, so jump back into it. During this part, again, this is going to be a little more technical, science-wise, so please interrupt if you have any questions. So I'm going to open up with talking a little bit about gravity and the Standard Model, as it's known, the Standard Model of particle physics, and why you should care. So it turns out gravity is sort of sitting off on its own. Even on this slide, it looks like it's hanging out with the rest. These three pieces of information, electricity and magnetism, the nuclear weak force, and the nuclear strong force, those comprise what is known as the Standard Model of particle physics. And I see in the little handout, the glossy handout you have, it probably talks about this. Gravity is by far the weakest force of all the forces that we know about. So there's four forces that make up our knowledge of physics: gravity, electricity, magnetism, the nuclear weak force, and the nuclear strong force. What's different about gravity from the rest is gravity only comes with one charge, so to speak. So you know, in electricity and magnetism, you have negatively charged electrons, positively charged protons, and it turns out there's a whole slew of other particles that have different charges. So they come in opposite charges, and the universe as a whole is electrically neutral. And one way you can tell just how powerful electricity and magnetism is as compared to gravity is you played with magnets, right? If you take a magnet and you just hold it near a fridge, it will jump out of your hand and hit the fridge and then hold itself there. Some tiny little amount of magnetism can withstand all the gravitational pressure from the Earth trying to pull the thing down. But it only comes in one sign. So that means all the stuff in the universe gravitationally attracts. Well, okay, maybe you've heard that's not quite true, but I'm starting off historically. Most of the stuff we knew up to 15 or so years ago, maybe a little earlier, more recently, all it does is it attracts. And so as you accumulate this matter and energy over the whole universe, it all pulls together. And that's why gravity is so important for our life, right? It keeps us stuck to the Earth. It keeps the Earth going around the sun orbiting the center of our galaxy hanging out in its cluster of galaxies, which is in a super cluster of galaxies. And then, you know, electricity and magnetism is also incredibly important. Like, this is why we're warm. We have sunlight. Photons, the sunlight from the sun, that's an electromagnetic wave. So that's obviously very important for our existence. And as I mentioned before, transistors come out of the theory of electricity and magnetism, computers, cell phones, etc. And I forgot to mention earlier, one of the reasons I like physics is it's the most fundamental of all the sciences. Like, in principle, everything comes out of physics. So one of the great triumphs of the early 1900s was understanding how to explain the periodic table of elements with physics. So that comes out of quantum mechanics and electricity and magnetism. And by electricity and magnetism, you notice I don't mention quantum mechanics on here. These three theories, electricity and magnetism, the nuclear weak force, and the nuclear strong force, which comprise the Standard Model, those are all quantum mechanical theories which have special relativity built into them. And that's why they're different from gravity. Every attempt we've made to make gravity quantum mechanical has failed. So we don't know how to include gravity with the rest of the Standard Model of particle physics. The nuclear weak force is responsible, for example, for radioactivity, which you've probably heard a lot about recently, especially here in hippie Berkeley. We're concerned about all the radiation coming over from Japan, from their nuclear meltdown. I can assure you I have people who know much more about this than I who are actually looking for these radiation levels, and you should not go out and buy iodine. You don't need to. Especially if you have an autoimmune disorder. Okay. Then there's the nuclear strong force, and this is responsible for binding all the protons and neutrons together into the nuclei, to creating the nucleus in the whole periodic table of elements. And of course, I'm realizing now I don't even have a picture of the periodic table of elements, which I'm probably more familiar to you, and I should have had one, but I don't. So, these three theories are the Standard Model, and then there's gravity. And people have been working very hard to figure out how to incorporate gravity into the Standard Model, but so far we've failed. the most relevant, of course, for everyday life is electricity, magnetism, and gravity. So we know gravity is important. Maybe you guys are all too young to remember Wile E. Coyote. Maybe he's come back on the TV, I can't remember. But I grew up watching this guy, and you'd see him over and over and over again have to relearn gravity. He'd just run off a cliff and continually fall down. He's got a hard life. The Roadrunner went to school, studied physics. If we didn't have gravity, Pac-Man would be very different. He wouldn't be able to successfully navigate the universe and eat the little pellets. So we know gravity is important, right? The whole galaxy that we live in is held together because of gravity. And then here's this picture of a supercluster centers of galaxies. So this is, again, just tangential. You look at what's called the Hubble Deep Field Images. So this is where NASA takes the Hubble telescope, points it to the darkest part of the sky, and looks as far back into the universe as possible. And you see this wonderful picture emerge, and it looks like there's just, thousands and thousands of stars. And it turns out only 4 of them are stars, and the rest are galaxies. And it's kind of insane. And then we get this picture where each spot here is a galaxy, right? And as I'll talk about very briefly, this sort of thin webs are predictions for the dark matter that we cannot see that are really helping bind the universe together. So another picture that's not here, this is all the visible matter in a galaxy, right? And one of the things we've learned is visible matter really only makes up 0.4% of all the stuff we can see out there. It's really kind of scary, right? We don't know what's out there. But anyway, electricity and magnetism are the electromagnetic and weak interaction. So this is the nuclear weak force and electricity and magnetism. We actually know that these are 2 parts of the same theory. So they've undergone what's called a phase transition. So a phase transition is very similar to when, water vapor turns into water or water turns into ice. So this theory has undergone a phase transition, and these 2 very different seeming interactions look very different. But we actually know, this is something we know for sure, they're part of the same theory. And you've probably heard of the Large Hadron Collider, the LHC, which is in Europe, in CERN, sitting between Switzerland and France. Yeah, get that right. It's a giant particle accelerator, 27 kilometers in diameter, the biggest one we as a species have ever built. And its goal is to take protons and accelerate them in opposite directions to 99 point, I can't remember how many, 99999% the speed of light. Smashes them together, and they're looking for the last piece of this electromagnetic theory called the Higgs mechanism, which will sort of unify this whole theory. So we've seen every single piece of this combined theory except for one particle, which may not exist, and then we'll have to rewrite the theory. But we know the 2 come together. We just don't know exactly how. So we go to smaller scale. So we start off with an atom. This is something we learned about back in the 1900s. And the electrons sort of orbit the center of the atom, which is known as the nucleus. And this is, of course, a big cartoon because this is all a quantum mechanical thing that's going on here, and you can't really draw a picture. You have what's called wave functions that have some probability density of describing if something exists here or there, and maybe it's over there instead. And so this is where all this uncertainty in quantum mechanics comes in. But this is a nice pictorial representation. We do know that there's something heavy at the very middle, and that these electrons are very far away. And I think the example is usually used is to say the city of Berkeley with a nucleus, the nearest electron would be off in New York. So that tells you almost all of the atom is completely empty space, right? So there's these electron clouds that sit very far away. And then we zoom in and we have a nucleus. We know the nucleus is made out of protons and neutrons. And another thing we've learned in the last half a century is that inside protons and neutrons there are other fundamental particles called quarks and gluons. So this is another part where it's fun, or maybe geeky to be a physicist. You get to name things. So I can't remember the quote for why it's called quarks, but somebody actually knew some literature and named these particles quarks, and it was Murray Gell-Mann who gave them the name. And then somebody else said, well, we know the nucleus is stuck together by some sort of glue, So we'll call it gluons. And that's how we got the name. So, you come up with some dumb name and it sticks. And now for the rest of history, we're going to know about quarks and gluons. So, yeah, the theory that describes the atom, turns out, is electromagnetism. And we know how to solve that theory very well. Its cousin is the theory that describes how the protons and neutrons bind together, and really at a deeper level how these quarks and gluons sort of interact and bind together. It looks as a theory very similar to electromagnetism, but it turns out we actually do not know how to solve it. You cannot solve it yet on pen and paper. And that's where the giant computers come in, which I'll get to. So, yeah, this is what I just said. Electricity and magnetism, the theory is known as quantum electrodynamics. And if you've heard the name, this guy Richard Feynman, who's a very famous American physicist, got the Nobel Prize with another famous American physicist, but that one's only famous to physicists, whereas Richard Feynman is known to popular culture because Richard Feynman, for example, was on the team of scientists who helped uncover why the Challenger space shuttle blew up when it was trying to launch up. And it's kind of sad because the very first public school teacher was on that shuttle, and kids all, you guys, this won't mean much to you, but I remember this. I was like 12 or something, I can't remember. And we were all glued to the TV watching this teacher launch up into space, and then the whole thing just blew up. And so the whole nation was kind of in shock for quite a while. And Richard Feynman helped uncover why the shuttle blew up. So he's famous for that and other reasons. I digress. So, quantum chromodynamics. This is the cousin theory. You can see even the name is very similar. And it's not an accident. This is the theory that describes the strong nuclear force. And this is what I'm going to focus on for my talk today. So quantum chromodynamics, or it's known as QCD for short, because inherently physicists are lazy and we like to make acronyms. So this is responsible for the binding of all the nuclei at the center of all the atoms. You get the neutron and the proton, which are individual nucleons. Nucleon meaning nucleus, so a nucleon is a singular piece of a nucleus. And the very simplest nucleus you can form is called deuterium. And this is just when a proton and a neutron form together. You might also have heard of this as heavy water, because this deuterium can capture one electron just like hydrogen. So chemically, in chemistry, it interacts exactly like hydrogen, except it's twice as heavy because the proton and the neutron basically have the same mass. And then it can capture yet another neutron and become tritium. So this one's bad for you because this is going to spit the neutron off, and you really don't want to be around a lot of free neutrons flying around. That's what causes your body harm. Well, that's one of the things that causes your body harm. I'm sure there's much more mundane things that you guys get into that cause you harm, but this one, if you hear about tritium warnings, you're going to stay away, that's bad. Okay, and then you get helium-3. So this is now 2 protons and 1 neutron. So this acts just like helium-4, its close cousin, but it turns out helium-4 is a very favored state in nature. It's much more favored than any of the others on this list here, in fact. And that's going to be important later in the talk. So then you get there's a whole lot of these, right? Like, you know the atomic periodic table of elements. Carbon-12, this is basically 3 helium-4 nuclei bound together. So this one's very important for life as we know it. We don't know of any way that complex life can evolve without carbon-12. And it's actually interesting, there's a puzzle. It took a while for us to understand how to go from helium-4 to carbon-12, because it turns out there's no bound nucleus with 8 nuclei, so 4 protons and 4 neutrons. That state is not bound together. If it's not bound, how do you get these 3 things to come together all at the exact same point at the same time and bind to form carbon-12? That was a mystery for a while. It's sort of like a bottleneck to produce all the heavy elements we know that exist in nature, like silicon, iron, lead, uranium, plutonium. Oxygen-16, of course, you're all fond of. This is now 4 helium-4 nuclei. And it turns out helium-4, as I said, is very favorable state in nature. And so every multiple of 4 for a while up this table of nuclei is a very favored state. And then you get to iron-56. This one's interesting because this is the last nucleus you can form through nuclear fusion and gain energy. So just, again, a small digression. There's nuclear fission energy and there's nuclear fusion energy. So fission is the one that produces lots of radioactive byproducts that are very bad for us. This is what's causing lots of problems in Japan. The 3 Mile Island or Chernobyl incidents all had fission plants. People are working very hard to build a fusion reactor. That's where you take nuclei and you smash them together and they release energy. If you could achieve that, you would basically have a clean source of energy. But the problem is it's so hard to smash these particles together and get them to bind. We haven't figured out a way to do that where you get more energy back than you put into it. But just to help you learn to differentiate between nuclear fusion and fission power. Fusion would be okay, but we can't do it. Fission has negative consequences if things go wrong. So iron-56 is the heaviest nucleus you can make through fusion and still get energy back. So that creates a puzzle. How do we see any of the nuclei which are heavier than iron-56? That's part of what I'm going to talk about today. Well, actually, we don't really know, for a while, we didn't know how to get any nuclei heavier than helium-4. Turns out if you look at the very early universe, which you can do by looking at giant gas clouds, which don't have lots of what we call metals in them. So metals are like all the elements in the middle of the periodic table. It's chemistry, I can't remember the names, but all the ones in the middle of the table. We didn't know, if you look at gas clouds without those elements, we know that it's sort of a pure form of a hydrogen-helium cloud that came from the early universe and wasn't polluted by stars exploding around it. And when we look at those, we actually know that the early universe is basically 75% hydrogen and 25% helium. So getting anything else requires some new phenomena. So what I want to tell you is, how does this very subatomic theory influence the universe that we see? And before I do that, though, I'm going to come back. Like I said, we actually know now that the things we look out and can observe in the universe with telescopes, and they emit photons and we can watch them, it's 0.4% of the stuff that we know has to be there. Absolutely nothing in this pie chart, right? And then if you add in the hydrogen and helium gas clouds that we can sort of observe, like through, if there's some galaxy shooting a lot of light, then that light gets reflected and refracted through the gas cloud, and so we can see them that way. And you add all that up, and the stuff that we know how to describe of all the stuff we know is out there, right? This is truly amazing. 23% of the stuff is we call dark matter. And what does that mean? That means it's just, we know it's gravitationally attractive. And the reason we can tell is there is you can look at galaxies and how fast the stars are spinning in these spiral galaxies. And you can tell, if you add up all the stuff you can see, it's not nearly enough to keep those galaxies together spinning at the rate they are. So that means we know there has to be a whole lot of dark matter. It's dark because it doesn't emit light. It doesn't interact with the rest of the stuff, the 4% we know about. We have no idea what it is. Well, I shouldn't say it. We have some theories for what it is, but none of them have been experimentally verified. So basically, we don't know what that 23% is. But the important point is this all adds up to approximately 25% of the universe, and all that stuff is gravitationally attractive. And then the other thing we've learned in the last 15 years is, well, it turns out the universe isn't, as it's expanding, it's not slowing down as it would. So it'd blow up and expand and kind of slow down if everything in the universe was gravitationally attractive. What we've actually learned is that the expansion of the universe has been speeding up for the last 15 years. So if you're around 10 billion years from now, you might get ripped apart because the universe starts spreading apart too fast. And that's what we call dark energy. And here we really have no idea what that is. This has sort of an anti-gravitational effect. It's a pressure that pushes things apart. So all we know is we can look at these stars that explode in the universe, and we can tell how fast things are expanding. And from that, we can infer there has to be this dark energy pushing everything apart. So I'm not going to talk about anything but the little bit of 4% here. That's what I'm talking about today. But there's this huge wide open field of exciting physics and astrophysics that is left to be answered. So let me move back to this picture. I'm sure you guys have seen this a few times in your program here. It's sort of, I find it, motivational picture. So the idea here is we have some big bang. So the whole universe is compressed to a size much smaller than a proton. For some reason, it decides to expand in a big bang and undergoes a rapid period of inflation where the universe stretches out faster than light can travel. And that's important, right? So the universe, the space between all the stuff, it's not that stuff is moving, but the space between the stuff actually stretches. And it stretches faster than light can travel. And that's important because light, as we know, nothing can travel faster than the speed of light, which means the speed of light is the speed that information can propagate, right? So if nothing can go faster than the speed of light, that means if the universe is expanding faster than the speed of light, if things look the same here, because they were in some sort of equilibrium, and then expanded suddenly really fast, they'd still look the same because no information can propagate between them fast enough to change things. That's an important thing. That's why I'm blanking on his name. The guy who invented the theory of inflation was at MIT. You guys probably don't care anyway. Yeah, Alan Guth. Thank you. Okay. And then there's this next period that's sort of important for us called this is the period of recombination, as it's called. I'll tell you more about that in a second. But this is what George Smoot actually got the Nobel Prize for, is understanding this period of time in the evolution of the universe. And anyway, so then the universe expands. It takes quite a while. There's a period called the Dark Ages, which are not the same as the Renaissance. Dark Ages happened before the Renaissance in medieval Europe. And then the universe expands slowly, and this is what we're seeing now. In the very end, it's accelerating, right? So this is time. We know the universe is basically 13.7 billion years old. So now what I want to do is I want to tell you where this theory of quantum chromodynamics, QCD, how it fits into this evolutionary picture of the universe. And just to remind you, as humans, we only exist in the very, very last sliver of time here. So we're like, you can't draw it with a pencil, it's too small. So maybe we can dim the lights a little in the front for the screen. There. Hopefully we keep them on in the back so people are less likely to fall asleep. There we go. All right, great. So the very first point that this theory of QCD is important is just when the universe is 1 trillion degrees Kelvin. And for all you Americans, that's basically 1 trillion degrees Fahrenheit. It doesn't matter at this point. It's so hot. The conversion factor, is all, factor of 2, it's okay. This is when the universe was 30 microseconds old, 10 to the minus 5 times 3 seconds. So very, very short time. That's sort of the first point QCD plays an important role. This period of time in the universe is actually explored by an experimental program out at Brookhaven on Long Island, New York, called the Relativistic Heavy Ion Collider. So this experiment takes gold and lead nuclei, accelerates them up to very high energies, and then smashes them together. And the electricity to run this thing is so expensive, there's a point where the government couldn't pay for it. And I can't remember who it is again, some wealthy person was so in love with this, he donated the money, something like $10 million, to pay the electricity bill 1 year to keep the experiment running. So what happens is you take these gold nuclei and you accelerate them to a really high velocity, close to the speed of light. And if you've learned at all about special relativity, as you accelerate things, funny things happen called Lorentz contraction, where the shape of things gets distorted to different observers. And these nuclei basically look like pancakes. And they smash together. There's some collision where these things interact, and most of them don't. And then, a whole lot of stuff happens. You create this really hot gas of quarks and gluons. And then as it spreads out, the quarks and gluons bind back together into the hadron, or the protons and neutrons we know about. And then here's a typical picture from this experiment. And so there's actually a lot of people at this lab who work on this experiment. The next period of time that's really important happened when the universe has cooled off to only 1 billion degrees Kelvin, or about 3 minutes after the evolution of the universe. And I'll come back to this. If something special didn't happen at this time, we wouldn't be here to think about it. And then the next important time, this doesn't have to do with quantum chromodynamics, but it's electromagnetic cousin quantum electrodynamics. This is the period of recombination, which happened about 380,000 years after the Big Bang. So this is when hydrogen and helium atoms can form. And what I mean by that is the universe has expanded, and as it expands, it gets colder. It's expanded and cooled off to the point where the electrons can actually get captured onto the protons, the helium nuclei, and form electrically neutral objects. So every time before here, there's like electrons and anti-electrons flying around, and so photons don't get very far. They propagate and they keep interacting with things and bouncing around. But then at some point, the universe cools, and all the electrons get captured onto the nuclei, and suddenly the photons can propagate freely throughout the universe. And so that's this point of recombination, and that's what's known as the cosmic microwave background. So that's 2 Nobel Prizes came out for this. One in the 64s for the guys at Bell Labs who were seeing these funny signals on their detector, and they thought maybe it's the bird poop up there, we'll go clean it off, and lo and behold, the signal was still there. It turned out to be the cosmic microwave background, which really helps confirm, well, that combined with the more recent work looking at the fluctuations of this background, confirmed the whole picture of inflation. And this happened when the universe had cooled to a mere 10,000 degrees, which is, you know, pretty cool, right? That's not too hot. And this is about 380,000 years after the Big Bang. And so here is this picture. And this is really where the quarks, the standard model of particle physics, fits in to the evolution of the universe. So what this is a picture of the cosmic microwave background. And what you've done is you've removed everything that looks the same. And these colors represent the very small fluctuations, the anisotropy in this cosmic microwave background. And these are on the order of 1 part in 100,000. So these are quantum mechanical fluctuations. This is where the fundamental subatomic world influences gravity, because these little fluctuations are going to become the seeds that form the galaxies as the universe keeps expanding. So 200 million years for gravity to take all this electrically neutral matter. So now the protons don't repel each other anymore because they have electrons, are electrically neutral, so they can just start falling into each other. Right? So the small density fluctuations, or energy hotspots, they're more attractive, and so they start to suck other matter in, and gravity takes 200 million years basically for gravity to suck all this hydrogen and helium together and create the first stars. And the first stars form in roughly 200 million years after the Big Bang. And then on this picture, our solar system forms out here something like 9 billion years after the Big Bang. And then this theory also plays a very important role. Basically, once stars are created, 2 modern days, and for as long as we're going to be alive, and a bit longer than that, this theory of quantum chromodynamics plays an important role in how the nuclei are created, which are important for life, how stars form, and how stars explode. So now I'll go back to each of these periods and describe in a little more detail how this theory, or the points where it plays an important role. So first, we go back to how do we get from quarks and gluons to protons and neutrons? And this again is when the universe is 1 trillion degrees Kelvin, 30 microseconds after the Big Bang. So basically, as the universe, of course they had to make it, it's going to grow much bigger than this in this time, but there's just a nice little picture. You have an early time where the universe is small and hot. When it's small and hot, these quarks and gluons are sort of free particles. They're not binding together, but they're interacting. And then as it cools off by expanding, the theory, or the universe, undergoes a phase transition. And again, a phase transition is really just meaning you have the same stuff, like steam and water, but it cools off. The steam cools off and it forms water droplets. And that's sort of like what's happening here. And then, you cool water off even more, it forms ice. Well, that's not, really what's happening here, but that's the idea of a phase transition. So we go at some temperature, which we know is about trillion degrees Kelvin, the quarks and gluons suddenly bind together. They're no longer free. They can't propagate off infinitely far away. They're bound together into protons and neutrons.
Can you explain to me why the temperature decreases?
Basically because you got a small volume and all this stuff is forced to interact. And as you make the volume of the universe bigger, things get farther apart. And so they can't exchange energy by interacting. And so temperature is directly a measure of how much things are interacting together and bouncing off each other. And so as you expand, you have the same amount of stuff, you make the volume bigger, and so each particle has more room to move around. So the temperature goes down. Does that make sense?
Well,
No, that's exactly what I mean, sorry.
so I mean, if you expand, unless the system is doing work on something outside, why would your temperature go down?
Well, it's because the universe itself is stretching, so it's not really doing work on anything. Basically, you take a bunch of stuff and you compress it, it's going to get heated up. You let it expand, it's going to cool off. Well, ask me again if that doesn't make sense. Okay. So going back to the Large Hadron Collider at CERN, the primary effort, like I said, is to understand how the electromagnetic and weak forces unify. And it turns out this is also responsible for giving each of the quarks a mass. But you'll also probe conditions similar to the Big Bang. And this is actually exciting for me because this experiment is turned on now. The year between when I was an undergraduate and a graduate student, I actually helped build one of the detectors there, the Atlas detector. I don't know if you can see it, there's this little piece here that I helped build. Anyway, I did help work on it. That part is true. What do we know? So these units aren't going to mean anything to you. All you need to care about is the relative value. These are mega electron volts. So electron volt is just a unit of energy that makes sense for the electron. It doesn't make sense for us because we're so much bigger than electrons. And mega is a million, right? So 10 to the 6 electron volts. If I look at a proton, which is a bound state of 2 up quarks and a down quark, I know the mass experimentally is 938 mega electron volts. Whereas I know the mass of the quarks that go inside of it are 2 mega electron volts for the up quark and 5 for the down quark. But another thing we know is if I take those quark masses and I send them to 0, so of course the first thing you see is if I do 2 times the up quark mass plus 1 times the down quark mass, that doesn't come anywhere close to 938 mega electron volts. What I do know is if I take those masses and I send them to 0, the proton mass drops to about 900 mega electron volts. And you also see that 938 minus 5 minus 2 minus 2 is not 900. And that's because there's a lot of strong dynamics. The gluons that I've mentioned are really have a big influence here, and those are giving most of the mass of the proton. But what does that mean? That means 95% of the mass of the proton would exist if the up quark mass and the down quark mass was 0. So that means 95% of the mass that we know about in the universe simply comes from this theory, quantum chromodynamics, the gluons running around and interacting with each other, trying to glue together, basically. So, as I like to think about my particle physics friends who look for the Higgs boson, they're sort of focused on, this little picture, and I kind of like to think about the bigger picture here. Doesn't seem to be working. All right. So it kind of ruined my joke. It's all right. You get the point. Okay. Big Bang nucleosynthesis, the next point of the universe. The universe cools off to 1 billion degrees Kelvin, about 3 minutes after the universe forms. So the first question we have to ask is, why is there even matter? So it turns out the theory of the standard model of particle physics is symmetric in matter and antimatter. It basically predicts a very equal amount of matter and antimatter. But we're here, and we're made out of matter, so we know there has to be a slight imbalance. There has to be slightly more matter than antimatter. So at the very early universe, you have a bunch of quarks and antiquarks, and then they combine together, they disappear into the vacuum and create gluons or photons or radiation. And as time evolves, basically all of these things, if there's an equal amount of matter and antimatter, they come together and they just form a bunch of photons. And so the universe would only be a bunch of photons if everything were exactly equal. But as I said, we know that can't be the case because we're here and we exist to think about it. But we do know that the answer for how there's more matter than antimatter actually must most likely come from beyond our current understanding of physics. So it's something we haven't figured out yet. What we do know is as the universe cooled, there's this imbalance of matter. There was roughly an equal number of protons and neutrons. But another thing we know about is as systems cool down, they sort of de-excite into the lowest energy state possible. And another thing we know is the neutron is more energetic than the proton. And in fact, if you take a neutron all on its own, it only lives for about 10 minutes on average before it will decay into a proton. So that creates another puzzle. If the neutron will decay into a proton, why are there any neutrons left in the universe at all? So this is what I was talking about before. If nothing interesting were to happen, we know we wouldn't be here to exist because there'd only be, we know the universe would look very different. In fact, we probably still exist. But what we do know is that it turns out, like I said before, there's this deuterium, or a bound state of a proton and a neutron. So if you imagine a system where you have two neutrons, one decays to a proton, the other could decay to a proton as well, so you have two protons left. But it's more energetically favorable for a proton and a neutron to combine into the first nucleus, deuterium. And you get about 2.2 mega electron volts of binding. So just, I'm using MeV throughout so you can keep some sort of relevant scale in your head. So the answer to why the universe looks like it does is the formation of the first nucleus, deuterium. So it turns out when a neutron binds with a proton, it now is energetically favorable for it to live. So bound neutrons don't decay. A neutron that's free will decay in about 10 minutes. So this is what's known as the deuterium bottleneck. And it turns out, so you take a proton and a neutron and you form deuterium plus a photon. But this reaction, which looks very similar to like a chemistry reaction, early in the universe there's like, what is it? There are 1 billion photons for every proton or neutron. And so that means these photons can easily come back, hit the deuterium, and break it back up into a proton and neutron. And that reaction goes in equal rates both directions. So you can't form deuterium until the universe expands and cools off even more, and the average energy of the photon drops so that they're no longer energetic enough to break the deuterium up. And that happens when the universe is cooled at about 100 kilo-electron volts, or about 3 minutes after the Big Bang, at which point that reaction only goes one way. The protons and neutrons bind into deuterium. And once you do that, then you open up the way to make helium. So once you have deuterium, you can then form tritium, and then you can capture the last proton and get helium. And so here, when you go from 2 free neutrons and 2 free protons, and you make a helium nucleus, you gain 28.3 mega electron volts. That's nuclear fusion that I was talking about earlier. So when these nuclei bind together, they release this much energy. And this is why stars are stable. They're trying to gravitationally collapse, but they keep burning hydrogen and stuff to form helium. Well, so I'll get to that later, sorry. This is sort of this is how the universe evolved in its early stage. You get protons and neutrons decay, and then eventually you get helium and hydrogen. In helium, one way you can think about why it's so stable is you probably learned from chemistry, you have electrons that can be spin up and spin down. And you can pick one spin up and spin down electron in the ground S shell of an atomic nucleus. And in the same way, you can take a proton spin up and a proton spin down, and a neutron spin up and a neutron spin down, and that state will allow itself to collapse to the most tightly bound state. And that's sort of why helium is so stable. But what we do know is the universe at its early stage was roughly 75% hydrogen and 25% helium, or there's 1 neutron for every 7 protons. And this is very sensitive to that deuterium binding energy. And this is where the theory of quantum chromodynamics comes into play. So the binding energy deuterium is 2.22 and some mega electron volts. It turns out most nuclei, like oxygen, helium, they have a binding energy of 8 mega electron volts per nucleon. So if I take deuterium and divide it by 2, because there's a proton and a neutron, this is only 1 MeV, 1 mega electron volt per nucleon. So that's like a factor of 10 smaller than is normal. So this is what we call a finely tuned system. If the universe were even more finely tuned, and this all depends on the properties of quantum chromodynamics, all the neutrons would decay because the deuterium you wouldn't gain enough energy by sticking a neutron into a proton. And what that means is you'd have mostly hydrogen stars like our sun. And that'd be okay for us because we'd probably still be here to think about it. But if you had a more natural situation where the binding energy is more typical, then what that means is all the neutrons would get captured into deuterium and helium, and the early universe, there'd be barely any hydrogen. You'd only have helium. And then we would not exist because you need hydrogen stars because they're very stable in order to have a planet like ours that has life. And so what we'd really like to do is understand how does this emerge from this fundamental theory of quantum chromodynamics. And here's in fact, it's not even moving. Right, anyway, so I wrote this on a little computer program, very, very simple, not sophisticated. The thing I wanted you to capture from that is you notice this quantity V naught only changed a very little bit. That's a variation in the fundamental parameters of the theory. Whereas this physical quantity A, you notice changed dramatically. It went off to infinity, came back around. This is an example of a finely tuned system. A small change in the fundamental parameters can cause a very big change in the observed phenomenon. So it turns out nature happens to be in such a finely tuned system. We know if you look at a proton and a neutron and how they interact with each other, in some cases they have this interaction with a very large A. This A is called a scattering length, which basically tells you the strength that these things interact with. And then in the channel where the deuteron lives, deuterium, this bound nucleus, you also have a large scattering length, but it's positive instead of negative. And when I say large, of course, I have to compare that to something. And what it's large compared to is the range of the nuclear force. So the nuclear force is very small, 1.4 femtometers, which is 1.4 times 10 to the minus 15 meters. It's very, very, very small. So this is what's happening at the nuclear scale. But this scattering length turns out to be noticeably bigger. And so we know that the universe is in this finely tuned system. And so if we can understand this fundamental theory of quantum chromodynamics, it will help us understand how this fine tuning emerges from nature, which is crucial to the amount of hydrogen and helium we observe in the early universe, which gets us to where we are. All right, so the next time is, this is the formation of stars, or solar fusion. And this is, again, when the universe is now cooled off. So it's only about 20 degrees Kelvin. So now you'd want to put on a few sweaters. This is pretty cold. It's about 200 million years after the Big Bang. So basically, in order to make the heavier elements, you have to have neutrons. So how do you get neutrons? Because I said there's only 1 neutron for every 7 protons in the early universe. Well, it turns out the way we get it is basically how our sun creates energy. It's through proton-proton fusion. So in fact, this turns out to need both the strong and the weak nuclear forces. So basically, imagine a scenario where you start off with 6 protons. They're just hanging out in the center of the sun. Well, it turns out you can gain a little energy by converting one of those protons to a neutron, forming deuterium, and spitting off a particle called a neutrino, which I won't talk about at all. And then you gain a little bit of energy, and then from there you can form 2 deuterium nuclei, and then each of those can capture another proton and form helium-3. So you have 2 helium-3 nuclei, and that will capture and create helium-4 plus 2 protons. So this is one of the ways the sun takes protons, converts it into helium-4 plus protons. And so when you do this, you gain a lot of energy. So again, this is how the star supports itself under its gravitational weight. This nuclear fusion process is how the sun stays alive. And this is what we'd like to be able to do on the Earth so we can make some free energy, but we can't do it yet. Turns out 80% of all the stars in the universe get their energy this way. It's proton-proton fusion. And the sun is a hot thing. It makes you warm, it burns your sun, or it burns your skin, doesn't burn the sun. But it turns out at the very center, it's a pretty pathetic generator of heat. So this doesn't mean much to you. It generates only 275 watts per cubic meter of stuff, which, since you live in Berkeley, you'll know that's basically a compost heap of the same size. So those little green bins you stuck all your food compost into, and they collect them, they get, 1 cubic meter. That creates as much energy as the sun. Of course, the sun is just so gargantuanly big, that's how it's able to heat up the solar system and give us life on Earth. And it's very slow, this burning of proton-proton fusion. And that's why the sun has been around for 4.5 billion years, and will be around for another 5 billion years before it blows, or gets really big and engulfs the Earth as a red giant. And that's very lucky for us, of course. But you cannot actually measure this very fundamental reaction. Because you imagine you're taking 2 protons and you try to stick them together, they're electrically charged, and so as you try to smash them together, the electromagnetic interaction is just going to send them to fly off. You can't get them to overcome this electromagnetic barrier and fuse. So anyway, if we can solve this fundamental theory, we'll be able to understand how this very important reaction occurs in the center of the sun. So how do you make bigger stars? Well, you need higher temperatures, which means you need more massive stars, because now you have to burn helium. A hydrogen star has exhausted all the proton fuel and it's turned into only helium. Then the gravity will pull everything in more until it gets hot enough so that you can burn helium. And the way that happens is, so if it's not hot enough, these 3 helium nuclei will just hang out happily independently. But we know as you heat up a system, it turns out there's an unbound state. So here I was talking about fine tunings before on the order of 1 mega electron volt. Now this is 0.09 mega electron volts. And now I have 8 nuclei instead of 1. So this is 100 times more finely tuned than creating deuterium itself. So this is getting incredibly finely tuned, meaning it's not something you would naturally expect to happen. And so when you heat the star up by compressing it, it becomes hot enough to form this state of beryllium, and then it turns out there's an excited state of carbon-12, and that carbon-12 can emit a photon and radiate down and form the bound carbon-12 that basically is the basis for life as we know it. So we'd really like to understand, is this pure chance? Is there some fundamental reason? Like if we change the fundamental parameters of the theory, will this scenario change? How much are we allowed to change those parameters before this whole picture falls apart and we're not here to think about it anymore? So again, this is coming back to, if we can solve the fundamental theory of quantum thermodynamics, we can start to address these questions. So this sort of fusion burning keeps happening as stars get bigger and bigger. As they get more massive and burn, they tend to burn even faster because they get so heavy, they burn really fast. In order to support the gravitational weight, it has to create a lot of energy quickly. And the heavier the nuclei get, the less energy you get by fusing, so you have to burn more and more of the stuff, so your fuel goes really fast. And this occurs, so in the very outside layer you have this hydrogen level, and then you burn and you form helium, and you get this weird onion layer. So the more dense the nucleus is, the deeper it falls into the gravitational well, because it has to fall in farther to get hot enough to burn. And so you sort of burn hydrogen and helium this way until you create carbon, oxygen, silicon. And as I mentioned before, you get up to iron, where you can no longer get energy out. And that's, yeah.
I'm a little confused about the fine-tuning.
Yeah.
So fine-tuning, am I right to say that it allows this fusion of elements to occur? So only when stars have become finely tuned are they going to go from, instead of the helium, into deeper and heavier elements?
So the fine tuning, they will fuse with or without fine tuning. What the fine tuning tells you is how quickly they fuse. Yeah. So what's really important is the fine tuning is why it takes so long for the protons to come together and form deuterium.
I think it would probably help with a little digression on what physicists mean by that.
By fine tuning. Yeah, digression in my brain. I have to go back 12 years or so to remember what I thought. Yeah. A Ferrari is a very finely tuned machine, right? Everything has to be just right. You drive the car, you go really fast, and then you got to take it to the mechanic after one drive, because everything has to be in sort of perfect alignment for the thing to work. That's sort of, I mean, it's not quite fine tuning in the same sense, but that's basically what I mean. Like, if things are natural, you don't have to be very precise, and things are just going to work the way they should. Like, hydrogen is not finely tuned. When you have a finely tuned system, everything has to fall in sort of perfect alignment in order for the process to occur. And so, for example, if this beryllium-8 resonance didn't have exactly this energy, then you wouldn't be able to form carbon-12, because you have to have a carbon-12 excited nucleus at exactly this energy so that it can radiate a photon and collapse down a bound carbon-12. So if it weren't finely tuned, either beryllium-8 would just bind together on its own and you just produce a lot of carbon-12, or it'd take more energy and the star would have to be more massive. You'd have to heat it up more or something. So, does that help? No.
I guess so is there a fine tuner?
Yeah, so you'd like to ask that question. Is there a fine tuner? So this would get into intelligent design, for example. I believe that these fine tunings are accidents, and we just like to understand how they emerge from the fundamental theory. But this is my personal opinion. You're free to have whatever opinion you like. The difference, of course, is intelligent design is a theory you can't test, whereas this is one you can. If you can solve quantum chromodynamics, you can test these fine tunings in nature. Yes?
I thought I read somewhere some time ago that like the sun's actually not that efficient. You know, if you think about fusion, right? Proton, 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 proton fusion, right? But that is, yeah, like you said, proton, is the like when we think about like we can perform a fusion reaction with deuterium and tritium, and that's a great deal more energetic. Is that the case? Or because I thought that proton, basically what you're doing is you're creating deuterium and then you're fusing deuterium together.
The reason it's easier is because deuterium and tritium are heavier. And because they're heavier, as you push them towards each other, the electromagnetic force won't push them away as easily. Because F equals ma. So if the mass is bigger, it's harder to accelerate the thing. Yeah.
Back to the fine, just the previous question about whether or not there's a fine tuning and stuff. Is the fine tuning, and as you said, it is usually as more accidents. is this the obstacle that scientists are facing when they're trying to create fusion reactions? Are they trying to make
No.
these reactions happen?
So there, the fine tuning doesn't have much to do with it there. What's really blocking you is the electromagnetic interaction, which is much weaker than the nuclear interaction, but the electromagnetic interaction is very long ranged. Whereas the nuclear reaction only occurs in a very, very small distance. So in order to fuse things, you have to bring them together. They're electromagnetically repelling, and only when they get incredibly close, when the electromagnetic energy becomes really high to try to push them apart, you have to overcome this barrier to fuse. And that's, so it's not a fine tuning there. The fine tuning is, if you finally achieve that goal, how much energy do you get back? So I have approximately 10 more minutes. If you guys want to keep asking questions, I can, I could stop any point as well. Then you just missed my great conclusion. But, all right. So we form carbon-12. You make giant stars. You burn all these things until you get to iron, and then the star is stuck. What happens? Once you hit iron, you can't get any more energy out by sticking more helium on. And so that means there's absolutely nothing to support the iron core. It's just going to keep collapsing. And so what happens is the iron core, so here's a picture of the onion layer of the sun. The iron core bounces in and starts to collapse. And as the core collapses, at first it was holding the rest of the star up, but then the iron core collapses. And then at some point the rest of the star is going to realize there's nothing holding it up, and it's going to start to fall in as well. But as the iron core bounces down, it turns out the center of the nuclear force is very strongly repulsive. So this iron core falls in, bounces like, it's sort of like a rubber ball basically, and just bounces back out. And the iron core falls in, bounces back out, but as it's coming out, the rest of the star is falling on top of it. And so you get this incredible explosion. These are known as supernova, right? Where the star basically just goes under this giant explosion. So these are the brightest, or some of the brightest objects in the universe. So, and then coming back to Carl Sagan, why we exist. Without these supernova explosion, you wouldn't have any fluorine in your toothpaste. You wouldn't have any of the heavy elements in the solar system. You wouldn't have any uranium or lead or whatever. All this stuff comes from these stars collapsing, exploding, and shooting all this stuff out into the universe. So, one of the things we know about our solar system is because the amount of metals we have in our solar system, we know our solar system isn't a first generation solar system. We know it has to be at least second, most likely third. That means there has to be a lot of stars that used to exist here that exploded and ejected this material into the nearby neighborhood so that our planet could have the elements it does and we could exist. All right. One of the possible outcomes of these giant explosions is something called a neutron star. And so these things are just, ridiculous objects of nature. They're incredibly super dense. So you take the mass of the sun and you compress it to the size of the Bay Area, right? So before I said, most of the space between all the electrons is empty. So basically what you're doing with a neutron star is you're taking all those electron clouds, collapsing them, and you just take all these hydrogen and helium and everything, and it collapses to form one giant nucleus, basically. So 1 teaspoon of this stuff is like, a trillion tons. It's some insane amount of matter. So again, understanding the properties of these stars and how they form all comes back to understanding this very basic theory of quantum chromodynamics. Bosons, again, a physicist came up with a name, and particles called fermions. Now these are actually named after another famous physicist, Enrico Fermi, so it's kind of understandable how this name came about. Or I don't know about the bosons. So anyway, photons are bosons. They can happily coexist and mingle together. They're social particles. They exchange all the forces we know about. Whereas fermions, or what you're made out of, are antisocial. They do not want to exist in the same state. Again, this is why you can't have 2 spin-up electrons in the S shell of hydrogen. They have to be spin up and spin down. And so you try to stick a bunch of fermions into some sort of potential well where they get trapped, they're not going to occupy the same energy state, but they're going to get more, they're going to occupy higher and higher energy levels. And this is why you can sit in your chair, right? The reason you don't fall to the ground is because of this Fermi exclusion, or it's actually called a Pauli exclusion principle, because you're made out of fermions. So we know in the neutron stars, you pack a bunch of neutrons together, they're going to start getting in higher and higher energy states. But it turns out there's other states of matter called strange matter. And again, this is a physicist convention. It's called strange. It doesn't look like the normal world. And if there's an energy level that's lower, then you can actually, as you try to stick another neutron in, it's going to decay to this other state of matter. And so it's very puzzling. We don't know what's inside of a neutron star. We can't make one in a laboratory because they're too, massive. We can only think about them and look at them. But understanding exactly where this line form of matter, that will tell you whether when a star explodes it forms a neutron star or if it forms a black hole. So if you have more available strange matter to go into, it's easier to compress stuff together and you're more likely to form a black hole. Whereas if that line is higher and it's harder to put, or you get more energy and you stuff in, you get a neutron star because it's stiff. This Fermi repulsion will hold it up. All right, just a couple minutes on what do I do. I try to solve this fundamental theory of quantum chromodynamics using the world's biggest, baddest, fastest computers that are publicly available. Meaning, you probably know there's Livermore Lab, I think it's that way, where they do some classified research. I can't use those computers because they're behind the fence, so to speak. But there's also really big computers in Oakland that are part of the Berkeley lab. All right, what is the theory? It turns out it's a very simple theory, at least to write it down. I don't expect this to mean anything to you here. But this is the theory of QCD, quantum chromodynamics. That encodes everything. All this fantastic phenomena, like stars exploding, the universe expanding, all this comes out of QCD.
What do you call this equation?
This is called the Lagrangian.
Well, it's Lagrangian.
Yeah. So in this theory, you have quarks. Quarks happen to come in 3 colors, 6 flavors. So up and down, strange, charm, bottom, top. Again, physicists are making the names. You have gluons, which hold everything together. And then you have one coupling, G, which describes how strong all these things interact together. Okay, so photons have no colors. So photons don't interact. A gluon is like a photon, except it carries color. So it turns out the gluons can interact with themselves. And this is the key difference between electromagnetism and this theory of quantum chromodynamics. This sort of self-interaction. It makes the whole problem, this won't mean probably much to you, but nonlinear is the word for it. This is just an experimental observation. We can infer the number of colors based on smashing things together. We don't have an understanding for why it's 3 as opposed to 4. We don't ever observe quarks and gluons. They're bound together. How do you know they even exist? Well, I trust the 30 years of science behind me, all the experiments that happened. We have ways of inferring. If they weren't quarks and gluons, there certainly are things that act exactly like quarks and gluons. And so we could call them a duck or we could call them a bird, but we might as well just call them quarks and gluons because they have all the exact same properties you would predict that quarks and gluons have. So, why don't you observe them? Here I have a quark and an antiquark. So they come in, well, these are supposed to be equal and opposite colors. You try to pull them apart, the force between them is more like a rubber band. So as you try to pull these things farther and farther apart, you eventually get so much energy in this glue tube that lives between the quarks that you have enough energy to create a new particle and antiparticle. And that scale where that happens is, again, 10 to the minus 15 meters, so you're never going to see it. And that's why you can never observe a free quark and gluon. You pull things apart and just pop matter and antimatter out of the vacuum. Protons are made up of 2 up quarks and a down. Neutrons are made up of 1 up and 2 downs. It turns out, so how much quantum mechanics have you guys had? Do you know about the Heisenberg uncertainty principle? Probably not. Okay. It turns out energy is sort of inversely related to distance. So as you try to look at things in a shorter and shorter distance scale, it requires more and more energy, which is why the Large Hadron Collider is this 27-kilometer ring. You accelerate things into incredibly high energy, and that's what lets you look at the most small distance scales of how these things interact. It turns out this theory, at large distance scales, the coupling that tells you how they interact is big. So that's why you can't solve it. But as you make the distance scale very small, it becomes weak. And that limit, you can solve it on pen and paper. And because of that, that lets you put this theory on a computer, because you can take the universe and you can chop it up into a grid. You can chop space-time up into some finite grid where there's a smallest distance scale. We typically denote A. And there's a largest distance scale we denote L. And so you put the theory on the computer and you let the computer worry about the long distance, how everything interacts at the long distance scale. Because you know exactly what to write down at the short distance scale. You also typically create what's called periodic boundary conditions. And what that really means is you have Pac-Man boundary conditions. As you go around the universe, you come back around exactly as you started. And that's because we have a computer, it's finite. We can't really, do an infinite calculation of the real universe. We get to play with the world's biggest, fastest computers. Like I said, these two happen to live in Oakland. They're at the NERSC, National Energy Research Scientific Computing Center. There's a computer at Argonne National Lab. Why we'd stick a computer that gets 100 degrees in the summer, I don't know. You have a big electricity bill to cool it off. But then someone also stuck a computer at Oak Ridge in Tennessee, and another computer in I can't remember where Kraken. So again, physicists name the computers. You have Jaguar and Kraken. Those are some of the fastest computers available today. So then what you do is you take your proton, you stick it on the box, you stick 2 of them down, and we basically run these computers to understand how these things interact, so we can try to build up a picture and understand where the universe comes from. And so just sort of, the summary is, at this stage, just in the last couple of years, the computer programs and the algorithms and the size of the computers have gotten to the point where we can begin to actually answer some of these fundamental questions, for example, about our existence, and really connect this theory of quantum chromodynamics with what we observe in nature. And the computers of tomorrow will be able to understand much more exciting problems, and maybe one day we can actually simulate a neutron star in a big computer. Well, some people are doing it, just not for the most fundamental theory. So, okay, why do I like what I do? Once again, it's about the real world. So some of you probably have heard of string theory. String theory currently has no experimental test that can be done to check whether it's a real physical theory or it's just a mathematical construct. Whereas quantum chromodynamics it's something you can test. It's a real thing. It involves some, in my opinion, very deep questions about our universe. These fine tunings I was trying to talk about. It allows you to make predictions about things that are not known. Again, this is what science is exciting. You're not trying to do things that people know how to do. You're trying to explore a new frontier. You get to play with the world's biggest computers. If you like that, that's fun. If you don't, well, then you probably won't enjoy this line of work. You get to work with people all over the world in lots of different fields. If you look at how things are moving, by the time you guys are getting to the point where we're getting the research, you're going to have roughly 1 million times the computing power available to you than I have today. And so you're going to be able to do really exciting things in science. And of course, from the Department of Energy, it's a great field for training young people, because people who are really good with computers and science are going to be really crucial for the future of our society, not just for science, but for understanding more, really important things like climate, energy research, all these things. So, thank you.